Welcome everyone for the second session of RoboLaunch. And for this presentation, we have Professor Sylvia Herbert. Sylvia is an assistant professor in Mechanical and Aerospace Engineering at the University of California, San Diego, where she leads the Safe Autonomous Systems Lab. Prior to joining UCSD, she received her PhD in electrical engineering from UC Berkeley, where she studied with Professor Claire Tomlin on safe and efficient control of autonomous systems. And before that, she earned her bachelor's and master's at Drexel University in mechanical engineering. She's the recipient of the ONR Young Investigator Award, the Hellman Fellowship, the UCSD JSOE Early Career Faculty Award, UC Berkeley Chancellor's Fellowship, the NSF Graduate Research Fellowship, the UC Berkeley, well, it's a lot of awards, the UC Berkeley Outstanding Graduate Student Instructor Award, and the Berkeley EECS Demetri Angelakos Memorial Achievement Award for Altruism. So thank you, Sylvia, for making the time for us, and I'll hand it over to you.
Okay, wonderful. Thank you so much. Let me see if I can share my slides. One sec. Okay, I think that's working. Hi, okay, yes. So my name is Sylvia Herbert. I'm a professor at UC San Diego. This is how I try to bribe people to come out and visit us. And I started at the end of 2020, so I've been there for a few years now. And I like to work on safety for autonomous systems. And when I talk about a safety critical system, what I mean is one in which there exists the potential outcomes or failure modes that are deemed unacceptable. So typically because you will hurt something, damage something, cause loss of life, etc. Intuitively, we split up the state space, where by state space here, I mean all the conditions of the robot. So position, velocity, orientation that describe the motion of the robot. We split it up into three domains. We have the failure set. This is the set for which you have crashed. You have run into that tree. And then we have the unsafe set. So this is the set for which you haven't yet crashed, but you are going to, no matter what you try to do. And then the rest of it is safe. So for intuition, the failure set is all system states that are unacceptable. The unsafe set is the states from which it's not possible to avoid entering the failure. And here is a drone from my colleague Jaime Fizak, that's operating in a safe condition. Here's one that's operating in an unsafe condition. So note that it has not failed, but we all know what's going to happen in the next video frame, which is this. It's not sufficient. Oops, let me go back. When we have complex dynamics, it's not sufficient to just say avoid failure. You have to also say avoid the set of states for which you will inevitably end up failing. And this is the set that we're interested in characterizing, and we're interested in finding the control policy that keeps us outside of this set. The way that I have been trained on doing this is through something called Hamilton-Jacobi reachability analysis. And the idea of this is that you have some model of your system, and we'll talk about that issue of assuming that we have an explicit model of our system in a minute. But first, let's just assume it. And it's a function of the state of your system, so, position, velocity, orientation, the potential inputs to your system, as well as potential disturbances that act on your system. This can be just uncertainties that you have in your model, or this can actually be an explicit antagonistic disturbance, like another player that's working against you. And you assume that you have bounds on these two things. And then in that state space, let's say that you have some goal that you would like to reach. Alternatively, it could be some obstacle that you want to avoid. The first thing that we do for computing what we call the reachable set, or the set of states for which you can reach the goal, or the set of states for which you will inevitably hit an obstacle, is to define a cost function over this space. So I define a cost function that is positive outside of the goal in this case, so high cost when you're not inside the goal, and negative inside the goal, so low cost when you're inside the goal. And then we're going to build up what we call a value function, where the value is going to say, given some initial state and initial time, I want to find the minimum cost of trajectories of the system. By this, I mean, if I have a trajectory that's moving along in this space, I want to know if the minimum cost it ever reaches over time is negative. If it's negative, that means that the trajectory was able to enter the goal and achieve negative cost at some point. If at all times the trajectory has a positive cost, that means that at no point did it achieve negative cost. In other words, at no point did it achieve entering the goal. So to do this, we're going to say we want the minimum cost, that's L here, of our trajectories over time. Now I'm going to replace this little squiggly trajectory with our trajectory notation. That looks a lot scarier, but it's really just saying if I take an initial state, initial time, and apply a control signal and a disturbance signal, then I can query this trajectory at any time along the time horizon, so at some time t, and it will output the state that I'm at there. It's okay if that didn't quite parse, just know that this is the same as saying our trajectory. Okay, so we can start from an initial state and time and look at all the different trajectories and see if any of them end up inside of the goal. And we found that you actually don't need to look at literally every possible trajectory that could emanate from some initial condition. Instead, it's sufficient to ask if it's the best case trajectory able to reach the goal. So if under my best effort, I'm not able to reach the goal, then I'm certainly not going to be able to reach it under less than my best effort. And so for that, instead of evaluating every single trajectory, we can evaluate just one trajectory from each initial state and time. We can evaluate the optimal trajectory, where by optimal here, I mean that my control is going to do its best to minimize, this is an infimum, so minimize the cost and try to do gradient descent. And I assume that the disturbance, this antagonistic player, is trying to do the opposite. It's trying to maximize the cost and do gradient ascent. So this is a very complicated looking optimization problem at this point, but what it's going to do is just have a mapping from an initial state and an initial time to tell me under my best effort, will I be able to achieve that negative cost? Will I be able to achieve reaching into the goal? And that's what we want to compute. Now, in order to actually solve this optimization problem is a non-trivial thing to do. What we end up doing in this work is something called dynamic programming, which is basically just brute force evaluating these trajectories backwards over time. The way that we do this is using an update equation. I'm not going to go into the details of this update equation here, but if you are familiar with a Bellman backup from reinforcement learning, or if you're familiar with dynamic programming in general from optimal control, it's doing the same type of thing. If you're not familiar, don't worry about it. Just know that we're updating each point in space backwards in time. And what it looks like is this. So when I actually run this in the computer, this value function is being computed and it's growing backwards in time as I reason about within 10 seconds, will I be able to reach the goal? So it starts with in 1 second, will I be able to reach the goal? In 2 seconds, will I be able to reach the goal, etc. So this is my value function. Like I said, if I query an initial state and time, it will tell me whether or not I will be able to reach negative cost over time. If so, then the value will be negative. So I'm interested in all of these states for which that value is negative. So if I just shear off here at 0 and look at only the states for which the value is negative, that is the set. And that is my reachable tube. That is the set of states from which if I start inside of this, I'm guaranteed to be able to reach my goal. If this was instead an obstacle, then I would simply flip around who is trying to do gradient ascent and who's trying to do gradient descent. So I would say my control is trying to move up and trying to go away from the obstacle, and the disturbance is trying to go down. And instead, this set would describe the set of states for which the disturbance wins. Essentially, the disturbance is able to reach its goal, which for me is an obstacle. Okay, so I know I just threw a lot of math at you, but the high level message is that if we have a model of our system and we have some inputs and potentially some disturbances, we can kind of brute force compute that set of states for which we can reach a goal, or that unsafe set for which we will end up crashing into something. So that's nice. It provides these safety guarantees and also provides control policies because the gradient of that function tells us online what we need to do in order to be able to reach that goal or avoid that unsafe thing. We have various different toolboxes. I have a list of them here in Python and MATLAB and C++. But this work struggles with complex models and uncertain environments. So for the complex models thing, as I mentioned, we're kind of brute force using this dynamic programming concept, which means over my entire state space, position, velocities, orientations, I have to grid it up and compute this update equation everywhere in that space. So that means the more complicated my model is, the harder it is to update everywhere in that space. So instead of a realistic quadcopter model, we might have a very simplistic one, or instead of a real car model, we might have this very cartoonish one. Or instead of modeling a human body with a lot of accuracy, we might model them as, say, a double inverted pendulum, which does not capture everything about what a human can do. And so an analysis over these simple models may not translate to an analysis over the real type of model. There's a lot of work that we do on trying to get past this using various sampling-based approaches, various learning-based approaches, various like decomposition-based approaches in space and time, but it remains a struggle that we're working with. And the other thing is dealing with uncertainty, uncertain environments, uncertain models, et cetera. We talked about how we can put some uncertainty in our model into this disturbance and handle bounded disturbances. But if you make that bound really big and you assume that the worst case thing is happening at all times, so let's say the disturbance is wind, if we're assuming that hurricane conditions are happening at all times, then we end up really conservative. Whereas if we are overly optimistic and assume that there's no disturbances, then we can end up too optimistic and not capture the safety issues. Similarly, we can handle moving obstacles and actually incorporate that into the structure of this value function, which I think is really cool. But because it takes so long to compute, we would need to know how those obstacles were moving in advance, which is kind of a silly thing to assume when you're talking about moving around people or whatnot. And so we struggle a bit with uncertainty here. Another method that has been really popular in safety analysis is something called control barrier functions. And it's a very similar thing that it's trying to do, where it's trying to split the space into the things that are safe and the things that are unsafe. And its gradients tell you what direction to go in. And so when I was interviewing for jobs, a lot of people were asking me why I was doing this complicated Hamilton-Jacobi reachability when I could be doing this other seemingly more simple method called control barrier functions. And so when I showed up during COVID and tried to figure out how to be a professor, I spent a little while just sitting down and trying to actually understand the relationship between these two different methods of trying to produce these safe functions that you can use for safe control online. And the very high level of what I found out was that in each of these, we have to split this up into how you would initialize the construction of one of these functions, how you would actually create this function to use, and then how you would use this function online. And when I say online, I mean during execution, like how you would actually query what the safe control should be for the robot during an experiment. For initialization, on the control barrier function side, people typically either try to design these functions by hand, or they try to use something called data-driven approximation. So for example, you would get several trajectories of your robot. Some of them would crash, some of them would not crash. And based on that information of what was safe and what was not safe, try to fit this function that classifies the safe and unsafe states. For construction, there's no real general way of constructing these for nonlinear dynamic systems. These struggle in the same exact way as finding something called control Lyapunov functions. And so for nonlinear systems, especially ones that have control bounds or disturbance bounds, it's very hard to come up with these. As I mentioned, for certain types of systems, you may be able to do one of these approaches and be able to get a valid control barrier function. But in general, it's very hard to find one of these. On the other side, with reachability analysis, we initialize with that cost function that we talked about, and that was kind of distance to obstacles or failure sets. And we do that painful, brutal dynamic programming in order to compute that safety function. It's slow, but it's rigorous. So we can handle general systems, input and disturbance bounds, and you end up with this maximum safe set that you can stay within. Online, what you get by default out of my method is this optimal safe control that has this policy that the change in your function over time is never going to be negative. So your change in safety over time is never going to be negative. This sounds great, right? You're never going to decrease safety, but it actually can be a little bit frustrating. So this is saying that, let's say we start at this level of safety. So we're safe, we're not at zero, or at some positive level of safety. I must always maintain or increase that level of safety. So I essentially must always be running away from the boundary and always running away from obstacles. In order to mitigate this, sometimes we do something called least restrictive control, which instead we say, let's assume that our safety is at this boundary of zero. And when I'm safe, I can do whatever I want. And when I'm about to cross into negative safety, I override it with my safety control. And this works, okay, this is called least restrictive control, but you can end up with this like bouncing behavior as you're bouncing off of the edge of your safe set. And so you can end up with this kind of bouncing behavior. And so, oops, oh no, okay. Whereas on the control barrier function side of things, they solve for something slightly different. They say, try to use the smallest control effort or minimize the difference between the control and what you want to do, such that the change in my safety is greater than or equal to this minus gamma times our safety function, where this gamma is some positive constant. And so this is a little bit confusing, or was confusing to me. But what this is essentially saying is that instead of setting a straight line here or a straight line here, instead they're setting this curve, where this curve is based on this gamma term. So this is the curve that is v dot equals minus gamma v. And they're saying that my change in safety must always be above this curve. That means when I'm very safe, I can decrease my level of safety and go closer to obstacles. But as I get closer and closer to the boundary of safety, I need to override that more and more and maintain my safety. So this is kind of a nice, smooth trade-off between being able to do whatever you want, and as you get closer and closer to the obstacles, needing to override what you want to do with the safety override. And you end up with something like this. So this gives you a fast analysis and these nice, smooth trajectories. Okay, so I spent a while just figuring out the relationship between these two methods, and I felt like there were different strengths of each of these methods. So for example, on the control barrier function side of things, it's very neat that they can use either intelligent decisions about how to hand design the initialization of their function, or use data-driven approximations for how to create them. On the other hand, reachability is nice because we can actually generate these functions. And we have this general method for actually computing them and knowing that we have a valid function at the end. And then finally, the control barrier function, people have this nice way of trading off between the performance control, what you want to do when you're very safe, and the safety control, what you need to do when you get close to the obstacles. And so we spent a while in our group seeing if we can merge these approaches. So initialize with something using, let's say, neural networks, refine them using our slow but painful method, with the hope that by initializing with something that's close, we just have to refine them a tiny bit. And then online, using this nice quadratic program for doing this trade-off between being very safe and not being very safe. And so we've spent a while merging these different approaches and playing around with them. And can someone tell me how much time I have left? Okay, well, I will just keep going until someone tells me.
Sorry, I was muted. Yeah, 30 minutes.
Oh, I still have 30 minutes? Great. Okay, good. And since it's a slightly different format, I wanted to make sure. So in the end, what we can do is we can take some desired safety constraint, take into account the long-term effects of the dynamics, and get out that single scalar function from computing that will split things into safe and unsafe. So for example, if I'm trying to avoid this human, I can create this function in the relative space between the robot and the human that says when you're far enough away, you can move around safely. If that safety ever becomes negative, then you're unsafe. You might collide with the human. And so I can query a particular point. Its level will tell me the measure of safety. If it's positive, you're safe. If it's negative, it's unsafe. And its gradient will tell me the safe direction to go. So if you want to maintain safety, you want to generally move in this direction. So the way that we often will use this online is to, every time we see an obstacle, slap down one of these functions. So you have your nominal control that you would like to apply if you had no obstacles in your way. We'll call that U reference for your reference control. And then we slap down this function over every obstacle that we see. And we say the control that you should actually apply, U, you try to minimize the difference between that and your reference control. Try as much as possible to stick to your original trajectory such that you are safe with respect to each one of these obstacles. And so you might end up doing something like this instead. This is nice because you can kind of treat each person independently and put down an obstacle over each of them. But there are some problems associated with it. So techniques that I use, these like analytical or these dynamic programming based CBFs for pairwise collision avoidance of avoiding humans, tend to assume that all actions of the other agent are equally likely. So I'm assuming that a human might go forward, but they might, with equal probability, go backwards all of a sudden or go to the right all of a sudden, because I'm assuming this possible worst case scenario. And so because of that, you end up with these really crazy conservative sets of safety that says that human might go anywhere at any time, so you need to stay really far away from them. And so you end up taking these really long circuitous routes, or you may end up with this freezing the robot effect, where the robot is scared because there's a possibility that if everyone is trying to run into it, it will end up crashing. Now, if instead we use those data-driven control barrier functions of taking a bunch of training data of a robot navigating around people and then creating a function based on that, it'll be really sensitive to that training environment and may not be representative in other environments. So here's an example where a very simplistic one, where let's say I train in an environment with literally one person. Then I might learn some safety function that looks kind of like this. So it kind of assumes that humans generally walk forward, and so just stay out of the way of that in front of them. If I then apply this in an environment with more than one person, so let's say two people, and I just put down this function that I've learned over both of them, then I'm essentially assuming that humans can walk through each other because I have not learned any interaction effects about how humans actually move around each other. So I may think that a path like this is safe, when in reality, when this person moves around the other one, they will likely crash into me. The core issue there is that we want to maintain these independent CBFs for scaling reasons. By independent, I mean we want to be able to do that thing where we just see a human, we slap down this function, we see a human, we slap down this function, and we don't have to reason about the humans interacting between each other explicitly. This is really nice for scaling because we just consider each person independently and don't consider joint behavior between them. But on the other hand, we want to be able to encode these interaction effects between different humans. And by considering them completely independently, how can we reason about their interaction? So are these two desires completely at odds? In my mind, the answer was yes. But my colleague, Professor Sean Gao in computer science, had an idea. And he said, what if you are a robot and you're reasoning about a single human independently, but you know the context, you know that they are in a crowded environment. If you see them walk forward, then and you're asking, can I move in this direction? The answer is probably yes. Probably they'll continue walking forward and it's fine. If instead they suddenly deviate like this, and you're asking, can I move in this direction? Well, knowing the context that they're in a crowd, you might be able to reason that they're deviating because they are moving around another person. There's some interaction effect, and therefore moving in this direction is not safe. So the question is, by paying attention to the current and past states, so a little bit of history of one individual, can we infer interaction effects by seeing that they have gone straight and then suddenly deviated? Can we infer that they might be interacting with someone? So the idea is to train in an environment with multiple agents, but only reason about a single agent and what's going on with them. And anytime you crash with anybody, either this agent or somebody else, you consider that as a failure. So you keep track of what actions lead to collision versus safety and use this to train a pairwise control barrier function. We call this a sequential neural control barrier function. And the training procedure is like this. So first we use trajectory samples to get a rough landscape of the CBF. And so we end up with some very rough safety function like this. And then we resample around the boundary to refine it. I know that's very high level. I'm not going to go into all the details of it right now. The loss function, I will very briefly mention. It's saying that the loss is that the value of safe states is positive. So we want to make sure that if we were safe, that the value function should be positive there. The value of safe states, unsafe states should be negative. So if we end up crashing, you want to make sure that the value is unsafe there. And then the gradient should obey that quadratic program condition, that thing that says when you're very far away from the boundary of safety, you can do whatever you want. And as you get closer, you have to override with that safety condition. We did a bunch of training. So doing the initial, just taking the trajectory data that we have and training on that, our average path length goes down, but our collision rate gets kind of stuck. And once we refine around the boundary of that unsafe set, our collision rate goes down, our average path length goes up, but then over time it goes down as well. Here's the training and testing setup. So in simulation, we trained with 6 human pedestrians using the simulator called Orca. And then online in the lab, we trained with 2 humans. And then for evaluation, we randomly initialized the robot, humans, and control configurations. In simulation, we went up to 600, I think, people. So very different from the training environment. And then in the experiment, I forget how many grad students we found. So like 6 or so grad students. And if at any point in the trajectory, the robot either collides with a human or cannot find a safe control action, then we consider that full trajectory as a failure. We're still online going to do the same thing that we do often in controls, where we slap down one of these functions over each person. But now this function, the shape of this function, should implicitly encode information about how humans interact. So even though explicitly we're reasoning about each of them independently, implicitly through the shape of this function, we should be able to reason about the interaction effects between them. And here you can see the student projected down the level sets of that safety function on each of these humans. Here's our initial hardware demonstration. This is before we moved into our new building, so it's a fairly small room. We have the 2 humans moving around. The robot is trying to get to this goal over here. Ignore the battery holder. That is the battery holder right there. So we're training on environments like this. And then for testing, here we've got a bunch of grad students in there. We're try to move in this tight space around each other. And then we have the robot using its learned value functions over each pedestrian that it encounters. And you see that sometimes it has to deviate quite a bit. So over here, it has to go way over here in order to reach its goal rather than taking the nominal path like this. And then in simulation, we would train on 6 people, like I said, and then scale up to 600. And here's, I'm not going to go into all the baseline comparisons, but here's comparing to various different potential field or black box CBF methods. Our method was much better at that. And then here's comparing to model predictive control techniques, wherein we learned a function of the humans, and then we rolled this out and did sampling-based model predictive control with them, with 110 samples here. And then we also gave the model predictive control access to the true dynamics of the human. So if it knew everything, was an oracle, would you be able to avoid the humans? And so this is kind of like a lower bound for us of if we knew everything about what the humans would do, when is a crash inevitable? Because you might imagine with 600 people, in some cases, no matter what, you're going to crash. And then in blue is our method. And then here's comparison to different machine learning-based approaches. So here we used, for a navigation experiment, we used PPO. And so here again, we train on 6 people, and then we scale up to 600. Here's the collision rate for PPO. And then in blue is the collision rate of our method, where we used PPO as the reference control and then just overrode it with the safety function that we learned. And then over here for a lane changing environment, we use DQN. And again, we trained on six people and then scaled it up. And you see that DQN has a much higher collision rate than our method. So we were able to outperform both control theoretic methods and standard machine learning approach methods in these experiments. So in summary, we exploited that important observation that the spatial interaction patterns of multiple obstacles can actually be decomposed and predicted through sequential modeling of individual obstacles. So we're able to still infer implicitly the interaction effects, but being able to reason about them individually. We designed these models that incorporated that sequential modeling of individual obstacles so they can be composed in environments with an arbitrary number of obstacles online. And our next steps are a larger scale experimental validation now that we have a larger space, an analysis of the probabilistic safety properties of these methods, because once we did some data-driven based approaches, we lost all safety guarantees here. It works well in practice, but we don't have guarantees. And incorporate robustness to uncertainties from perception. So this paper ended up winning one of the best paper awards at one of the big robotics conferences last year. I think largely because of this key idea, and because using that we were able to, in environments where humans act similarly as what they do in the training environment, be able to outperform both the control methods and the machine learning methods. Oh, and consider other information that we can shove into this function. And then one next direction that we're exploring is we assumed that we could, we basically made the assumption that humans don't react to the robot in this work. This allowed us to do some data augmentation that allowed us to go back and kind of resample, asking, well, if my robot was here, would it have crashed? If it was here, would it have crashed? If it was here, would it have crashed? Using the data that we collected. But in reality, humans do respond to how the robot's moving. And there are a lot of other cases in which you physically have to reason about how the world reacts to the robot. So in one case is the student who's interested in this kind of rubble scenario where, let's say you have some disaster site and you need to be able to move things around in order to reach some goal. And you want to move them in such a way that they don't all collapse on you, the rubble, but you want to be able to reason about each piece individually. His rubble initially are these Pringles cans that are filled up with different amounts of mass and have different centers of mass, so are different levels of tippiness. And so when he pushes them around, he's trying to push them aside so that he can get through to the other side, but in such a way that he does not knock them over. And so he has to reason about being able to reach the goal without knocking over the Pringles cans. If now you have to reason about interaction effects, the fact that pushing one Pringles can knocks it into another one, can we similarly use this implicit interaction effect information into the structure of our safety function in order to reason about environments like this? So that's the next step of what we're exploring for this project right now. So with that, I'd like to thank my co-authors, and then I will stop and answer questions and chat. Thank you.
Well, thank you very much, Sylvia, for the talk. Yeah, we'll now start our Q&A session. Well, I'll ask everyone that has a question to come here so she can, so you'll be closer to the mic and she can hear you more clearly. please. So yeah, we can start now. So Killian, please. Yeah, you can come. Yeah, this will be faster. I'll just turn the camera so we can see who's asking.
Hi, I'm Killian. I guess so. I thought there were a lot of cool different aspects about your research, but the one thing I was confused about is how are you actually going about sensing like the human that you're actually inferring, and like what if they get obstructed by another human, or some basically how do you go about sensing the different obstacles?
Yeah, absolutely. So for the first initial experiments, we actually had each human wear a little tracker, so that way we didn't have to reason about that question. But that's the obvious next question. In fact, we have this project with this Japanese company that has these warehouses and construction sites, and they have warehouse robots, and they want to get those robots to not run into their employees. And so they're interested in applying the same methodology to their environments. And there, you can't necessarily assume that every human's wearing a tracker. And so for that, we're partnering up with Professor Henrik Christensen, who's working on perception-based techniques for how to keep track of different pedestrians. And you hit on exactly the right thing, where if they're occluded, the fact that we need to know a little bit of history of each pedestrian means that we have to have pretty good reasoning of when one person passes behind another person, that this was the same person that was over here. And so that is the tricky part about doing this in real world implementation that we are working on now.
Thank you.
Thank you.
Hello, Professor Herbert. I just had two quick questions. The first was, I heard that you're well involved with aerospace, and I was wondering, what are some aerospace applications you found in your work?
Oh, yeah, sure. Yeah, so I'm in the Mechanical and Aerospace Engineering department, and so we work on applications that range among them. So a lot of the applications that I think are of a lot of interest right now related to this is the dealing with the multi-agent coordination. So as we think about urban air mobility, we need to reason about a small aircraft that have to navigate around each other in tighter spaces and have to deal with environments that we maybe did not by standard deal with in a lot of aerospace applications, where when you're moving through, let's say, a city environment, the wind effects that you have from buildings and whatnot cause all sorts of new unexpected disturbances that happen to your system. And so I think that this is one big application domain that people are interested in. And then another one is in space robotics in general. So when you're out in space, you want to be extra safety critical about things. And so that's where algorithms that take more time but are more confident in what they're saying in terms of the safety related to that are very much still in need for that. And then at least at UCSD, when we talk about aerospace, we often also mean aeronautics as well, because we have a lot of ocean stuff going on. And so there's similarly a lot of really interesting things to explore in the ocean and underwater domain for safe autonomy. And so those are kind of, I guess, the directions that we most explore.
Great. And then the last question I had was, so it seems like your work does a lot of quick, nearly instantaneous calculations. How do you obtain enough computing power to suit all of your needs?
Oh, that's a great question. What we try to do is, as much as possible, offload most of the compute to the pre-computation, so constructing those functions. And then online, when you're just querying that function, it's actually a very, very fast and lightweight computation. So most of what we try to do is try to prepare ourselves ahead of time and then be able to not require a lot of compute online. Now, as we reason about more unexpected changes that you couldn't prepare for ahead of time, that you have to adapt to online, then you have to ask for algorithms that are a little bit more heavy duty. But we, as much as possible, try to keep ourselves from needing to do a lot of intense compute online.
Got it. Thank you so much.
Hello, I'm Abby. I was wondering if you've explored like function composition, like the HJR or CBF composition between two different robots in the same environment. Like if you've got like a quadcopter and then like a ground vehicle, if it's possible to combine like information about unsafe positions in the same environment.
Yes, yeah, you've hit on something that's a very like trendy topic right now called heterogeneous teams is the term, where you have like a team of robots, maybe a team of robots and people, and the different robots have different capabilities. Maybe some are ground, air, water, whatever. They have different sensing modes, they have different ways of actuating, and they all have to collectively complete some task. And you have to reason about who is the best person agent to go and do something and how should they share information across the different systems. And so we haven't yet for this particular application explored that, but I was just talking to my students had a ground robot experiment that they just finished and then a quadcopter experiment that they just finished. And I was like, maybe can you just throw them together and reason about what information you should share about safety. What information about can the aerial vehicle tell the ground robot about safety that's critical to it, but maybe not critical to the aerial vehicle. It can fly over some dangerous thing, but it can inform the ground vehicle about where it is and vice versa. Anyway, big, interesting area and definitely worth exploring and very much of interest both in the research fields as well as the funding fields right now. So you've hit on something good there.
Very cool. Thank you.
Hi, hello, Professor Herbert. My name is Hojun Kim, and thank you so much for the amazing presentation. I have three quick questions. First one is, you mentioned that in SN CBF, like we kind of train like to the offline training so that we give context for individual robots. But I was wondering how we can like still guarantee the safety or keep the forward invariance property of CBF if we are kind of training on doing the offline training with this data set. And I was wondering if it's like, if the result is like kind of dependent on the quality of data.
Sorry, can you ask the first part of that? I got the quality of data part, but the first part?
Yeah, so I was just wondering how like if we're doing the offline training, like how we can still kind of guarantee the safety.
Just this is a hard thing. It's going to depend on being able to reason about how effectively you were able to cover the space in terms of the data that you were able to collect of being able to split up that safety, the safe and unsafe region. So first, being able to have confidence that what you have learned is accurate for the training data itself. And then the second part of it that's even more tricky is reasoning about if what you are seeing online is similar enough to what you trained on, that it's valid to use the learned safety function. So for example, one way in which I could see this breaking pretty quickly is if you have, for example, I once talked to ClearPath Robotics, and they were saying that they had their warehouse robots that they might test in Canada, and then they go and deploy it in China, but people from these different cultures move slightly differently, like slightly different speeds, for example. And so just the policy, the underlying policy that the human is using may be different. And for that, you have this distribution shift that happens. And so you need to either have a rich diversity of data that you're training on, or be able to reason intelligently online about distribution shift and how you can adapt the safety function based on the differences in distribution. And these are both hard problems that people are definitely looking into trying to solve. But if you really want to be safe, then you need to go back to the assume everyone is out to get you version of worst case safety analysis that we do. And so you're always going to incur some risk if you're going to reduce the conservativeness there.
I see. Do we measure the confidence of that like prediction or safetiness, or
that's a great question. I in the past worked on a project with a professor at CMU, Professor Andrea Baichi, on a similar type of notion where we did reason about our confidence in how similar the human's actions were to our model of how a human works, which gave us a lot more, like a probabilistic safety guarantees and reasoning that we could do online. The main tricky part with that was that we had to have, in order to be able to do that computation online, we had to have such a simple model of how humans work in order to match whether the actions matched those models, that it wasn't very scalable to either lots of humans or more sophisticated models of humans. And so you have this trade-off again, where if I was deploying this in space, I would absolutely use that method instead. The reason is about confidence, because I really want to be very sure about what I'm doing. If I'm instead deploying this as like a little delivery bot on campus or something, where if it nudges into somebody every once in a while, that's okay, then I might be more okay with using this implicit stuff. And so it really depends on the context of what you're willing to do.
Got it. Thank you. And the second question, the last question will be, like, will it be able to use this and expand it to multi-robot system, or have you ever considered about like moving in that direction as well? Or
Yeah. I think it absolutely could be moved to a multi-robot system in a pretty straightforward way. And then, like the Abby was suggesting, even more interestingly, you could then ask if you have multi-robots where the robots are different in different ways, how do you then compose together these safety functions for them? Would be a really fun thing to explore. So yeah, I agree. Yes, on all of these things. We just haven't done them, but great ideas.
bye-bye.
Hello, my name's Chase Dunaway. I'm currently also working on a project related to CBFs at my time at risk. And I had a couple questions regarding applications and deployment in the real world, as well as some of the other factors that come into occurrence with CBFs. So I guess there are two questions. I'll formulate it this way. In real world applications, you kind of touched on this with the last question, such as autonomous cars. How do you balance safety guarantees and practical integration into society? So like maintaining 100% safety on a road is probably not what you want to see if you're late to work or something. But is this even realistic to have some sort of implicit method where there's other factors such as oversaturating your inputs or working with a system with a greater number of dimensions in which it's harder to train with?
Yeah, okay. So we're really interested in this direction in general. So one of the really cool things about a valid control barrier function, where I say that because often it's hard to find, again, a valid control barrier function, is that when you're outside of the safe set, it acts as what's called a control Lyapunov function. And so the same exact online algorithm will, when you're outside of safety, will exponentially drive you back into safety. And so one thing that we're interested in exploring is sort of layers of safety. So let's say, for example, you're an aircraft and you have some region within which if there's some engine failure, you can land safely. And so you have this very conservative region that you'd like to stay within if possible, because again, if there's some disaster that happens, you can land safely. But you sometimes need to leave that in order to get your performance that you need, in order to reach something that you need to get or whatever. And so when and how do you intentionally choose to violate the conservative safety guarantees in such a way that you leave that safe set, and so that you minimize risk while you're outside of the safe set and maximize your ability to stabilize back to the safe set? And similarly, if you have, like you said, conflicting constraints, like the robots need to stay close enough to maintain communication, but can't collide with each other and also shouldn't collide with obstacles, and they need to go through a narrow corridor. So they need to split up so that they can squeeze through a narrow corridor. How do you override the stay close to each other constraint in such a way that you maintain safety for the harder constraints, squeeze through the narrow corridor, and then regain safety with respect to the stay close to each other constraint? So in general, can we reason about these sort of layers of safety requirements and reason more importantly about how to leave safety intelligently? So leave one layer of safety for another layer of safety so that you can kind of squeeze back on the safety onion if need be. I'm happy to talk more about this. I've been thinking a lot about this kind of thing. A similar type of deal is with something like this, as I mentioned, as long as the behavior that you're seeing of the humans online matches what you trained in terms of how they generally move around people, then this should be valid. If people start acting differently, or if you notice a distribution shift, then it might be worth switching back into your more conservative safe set. And so similarly, how do you reason about when your training-based safety is no longer valid enough to rely on and you need to switch back? These are all open questions, but all, I think, very interesting and worth thinking about as we talk about wanting to maintain some rigorous reasoning about safety while wanting to also make these things practical for different types of applications.
Thank you.
Hey, well, I'm Leo, and my question is, when you think, well, safety is important in scenarios where the robot interacts with the humans, and the way you define the reachability optimization at the beginning, it looks like the external thing that we cannot control, which is the disturbance, is always trying to is always fighting against the robot, but in many human-robot interaction scenarios, we are interested in collaboration as well, where the disturbance would actually be helping the robot. And is this something that you can embed into this Hamilton-Jacobi reachability framework?
Yeah, absolutely. So if you know that the other agent is doing its best to help you and is acting optimally, then you simply turn that max into a min, and essentially they become another control input. And so it turns from a min-max game where you are antagonistic to a min-min game where you're both working together to do gradient descent. And so, but this would also assume that the other agent is acting optimally, so is doing the best thing for the goal that you want. If instead there's something in between, then you have to reason about how you mathematically describe that and then how you would fit that into the dynamics or the optimization.
Thank you.
Yeah, sure.
Hi, my name is Moo. I'm not sure if this is a relevant or like a fringe question, but like, let's say in a search and rescue scenario, of course, like the robot wants to be safe, but its ultimate goal is like the safety of the person it's trying to rescue. So like, if you're in like a collapsing building, for example, you want to be safe until you get to like where the person is, and then if there's like, I don't know, a rock, it's gonna fall on their head. You gotta, you're willing to like. Ideally, the robot would be able to sacrifice its own safety, or it has like some threshold over which it no longer is trying to be safe, and it's trying to prioritize the safety of who they're trying to rescue. And I don't know, is that relevant, or is there any like?
Absolutely, I think that comes back to the safety layers thing, where you want it's like the 3 laws of robotics, where you want the robot to maintain its own safety, but as a higher law, you want to make sure that it maintains the safety of people. And so if those are at a conflict where the robot has to sacrifice itself in order to save someone, you want to make sure that it does that. And a similar type of thing was actually pitched to me by a program manager at the Office of Naval Research, who was saying, you know, shipboard fires are a really big deal. If you have jet fuel that is caught on fire, this is a very scary and real thing that you have to deal with very quickly. And you want to make sure that the robot is staying safe with respect to the fire for itself, but if it's blocking a firefighter from being able to reach the fire by trying to keep its own safety, then clearly this is an issue. It should override its own safety for the sake of the firefighter being able to reach the fire. So you need to be able to have some contextual awareness and being able to understand priorities and stuff like this, which is a very complicated thing to ask, but very, very much a practical, important thing to reason about. And so this is where, again, we're starting to think about these safety layers thing, and how do you reason about when to shed a layer of safety in order to preserve the more important layers.
Okay, thank you.
And just to wrap up now, we have one question from the YouTube. And the question is, what's the meaning of larger scale experimental validation? If you can elaborate on that.
Oh, yeah, sure. So Henrik Christensen is the director of our Contextual Robotics Institute, and he has a lot of robots. And among them, he has several ground robots and aerial robots that he can use outdoors. And he has been using for like navigating around campus and collecting pedestrian data. And he has said that if we can get all of this working and get the funding for it, then we can actually try our algorithms on his robots outdoors among the college students, et cetera. And so that's what we're hoping to be able to move towards. Right now, we're working with him on this Japanese project that I mentioned with the warehouse robots. But that's still mostly in the lab. We haven't yet gone externally around humans, like normal college students.
Great. Well, thank you very much for the talk. And well, let's just. Well, again, thank you very much from all the RIS and RI community. And well, we can wrap up here. Take care. Thank you for answering all the questions and the presentation.
Thank you so much.
Bye-bye. Take care.